this book calls them transducers, which is okay. A transducer, if you looked up the definition, it's a device that takes one form of energy and converts it into another. So a sensor, so a paddle wheel would be a transducer, but it's not a sensor. So technically, a sensor is a transducer, but a transducer doesn't have to be a sensor. Yeah, but that's a transducer, that's a sensor. But a sensor, so a sensor is a transducer, but a transducer doesn't have to be a sensor. That would be like saying a Ford is a car, but a car don't have to be a Ford. Y'all understand that? So a transducer is any device that takes one form of energy and converts it into another. So technically this is okay, but transducers could fall into thousands of transducers. So what does a sensor do for us? So it does mimic. So our brain does not see, our brain does not feel, our brain does not smell, our brain translates chemical and electrical impulses to mean things. So basically our senses, and we say we have 5 basic senses, but there's a lot more, guys. There's a lot more than the 5. And we have nerves, and what does the nerves do? Well, it takes physical stimulus and converts it over to what? Electrical impulses. So our brain can do what? Process. So that's what these guys do. They take physical stimulus and converts it over to electrical quantities so we can process it. With computers, we could process it with programmable logic controllers, or we could process it with relay logic, we could process it with logic. So, examples, a device that converts energy from one form to the other: microphone, actuators, loudspeakers, thermometers, antennas, photocells, LEDs, light bulbs, windmills, touchscreens, electronic sensors, and the list could go on and on. I could say windmill, I could say anything. All those would be considered to be transducers. So our transducers are going to take, our sensors are going to take electrical stimuluses, converts it over to electrical impulses so we can process it with electrical devices or electrical and electronic devices. Are you okay? Does that make sense? Well, the book covers thermistors, it covers photoresistors, Hall effect, ultrasonic, I think piezoelectric. We're also going to look at photovoltaic. I think we're going to look at photodiodes, just to get a basic touch of a phototransistor. So we're going to look at a lot more sensors than the textbook actually covers. So a thermistor, and I went back, guys, and I was going to show y'all this, but we don't have, oh, maybe I do. Let's see if this guy here's something. A thermistor varies its resistance with temperature. So we know how that works because we played around with a diode. And I know if I reverse bias a diode and I heat it up, its internal resistance goes down. If I cool it down, the internal resistance goes up. We call it leakage. Well, I can take a piece of silicone just by itself and I could put a conductor across it or put a voltage across it and it would change its resistance to temperature. So we have 2 types of thermistors. We have what we call an NTC, which means a negative temperature coefficient, which means and what they're talking about is when R increases. So what they're saying, if temperature goes down, R goes up. So if temperature goes, for an NTC, if temperature goes up, what does R do? So NTC means they vary in opposite directions. PTC means they vary in the same direction. So in NTC, if temperature goes up, then R goes down. And of course, if temperature goes down, R goes up. These are probably the most popular out there. And they're very simple devices. They're basically just a semiconductor, a piece of semiconductors, with put inside of some type of case, like plastic or something like that, or ceramic. Positive temperature coefficient, resistance varies in the same direction with temperature. So the ones I have, I don't know if you got manometers, these guys are real hard to so small. And I was trying to find. I grabbed the wrong one. Their resistance, they're definitely going to be rated in wattage. And then of course they are going to be rated in a tolerance. And then they're going to be rated in degrees. What degrees range are they set up to handle? I would say so. Well, this is the one I have, and I don't remember the part number on it. I'll have to find it. It's going to be hard to see. So like I said, this right here is the thermistor. And then I'm going to bring a soldering iron against it. Because the resistance goes down, we know it's an NTC. Oops. And if the resistance goes up, when it starts cooling down, we know it's an RTC. So if I was to go out, so we could use this to literally measure a temperature, right? The problem, we do have little problems with it, and we'll show you that in a minute. So now we got to take this, it varies its resistance with temperature. We got to get something that varies, gives us an electrical signal with what it measures, right? You understand? Well, resistance is electrical, but it's not, we can't transmit resistance. The two things we can transmit, what's the three things that we have available to us besides power? We have voltage, current, and then of course right here it's resistance. I can't send resistance over wire. So that means we either need to have a way to convert this to a voltage or to convert it to a current. What's the most popular used? Probably voltage. So how would I take this? So the symbol for a thermistor is we start off with a resistor. This is one symbol. Then we put a line through it indicating it's variable. It usually indicates it's mechanically variable, but it's not. And then sometimes they'll put a T up here, indicates its temperature. I think I got the symbol. So let me see. Yeah. So this is the international symbol, the IEC symbol, International Electrotechnical Commission. Then this right here, this is not one, and this is not one. This would be one. No, these are the wrong things, guys. I don't have the symbol for these. So I've seen them with a T. I've seen them with a degree symbol up here. And then sometimes they'll put it in a circle and sometimes they won't. So this would be the symbol for this device. And how am I going to take that and convert that over to a voltage? Current is a little harder. So I've got this right here, and I need to get a voltage that changes the temperature so I can send it. Everybody got any ideas? No, I've got to take a resistance that changes the temperature and somehow get a voltage that changes the temperature. So how can I do that? Well, no, this is guys acting like a rheostat. So all I'm gonna do, guys, I can come up here and I can take a fixed resistor and put it here. Let me draw that a little better. It'd be better to drop from the bottom up. And maybe connect this to 10 volts. And then I'm gonna take my output right here. So it means temperature goes up. The total here's got to drop 10 volts, right? You understand that? Temperature goes up. This guy goes down. Means the voltage drops, which means I goes up because RT goes down. This guy drops less voltage. This guy drops more. So as the temperature goes up, then my output voltage would go down. If I wanted my output voltage to go up, I would take my temperature sensor and put it up here. And then I would come down here and put my fixed resistor down here. So it depends on what you want. So temperature goes up, R goes down, right? Voltage drops goes down. So here's R, here's V. It means the voltage drop down here has to go up. This R stays constant, right? So that means the voltage drop across here, the R across this resistor would go up. So now it depends on what you want. So if I put the temperature sensor at the bottom, then my output voltage would vary in the opposite direction. If I put the temperature sensor at the top, then my output voltage would change in the same direction. Everybody understand that? Very simple. This is the problem we have with the misters, is that they're not linear. So here's temperature, and of course this is an RTC. This is an NTC. Excuse me. So the temperature goes up, then R goes down, but it varies like this. We call that an exponential curve. So it doesn't vary at the same rate. So it's not a linear curve. To be able to really use this over an extremely large range, then somehow we would have to compensate for it electronically. But if I knew this curve right here, then I could program that into like a programmable controller or something to compensate for it. Usually what we do is we use it over a narrow range. So if I was to come over here and only use it between here and here, then that curve is pretty much well linear, right? So these are basically, if you've got an electronic thermostat in your house, what's the temperature range for your house? What usually range do we use to keep our temperature in? Between 70 and 65. I like mine real cold at night, so I cut my temperature down to 65 at night, and during the day we keep it like 72, 74. Well, see, that if you look at that, if you go between that range right there, I can't get it right here. But if you go between that range right there, then that curve right there is basically linear. So we use these things a lot on something that varies over a narrow range. Very cheap, very simple, very easy to change a voltage out. So thermistors are used. But I would not use these if the temperature had to change over a wide range, or if it had to be extremely accurate. Thermistors, pretty neat. So this shows you the basic circuit. The only problem I have is I cannot establish what is zero? What is zero? What temperature? How do I establish 70 degrees unless I can come up here and come up with some type of standard, right? You understand that? So how would we do that? Well, we use one of these guys. Called Wheatstone Bridge. Have we talked about this in this class yet? Did y'all study Wheatstone bridges in DC? I'm gonna have to really talk to my DC instructors. So this is probably one of the most popular DC circuits out there, especially when sensors come into play. So we come over here, and I'm going to redraw it. So that's the hard way to draw it. I'm going to draw it like it's actually wired. So I'm going to come over here, and I'm going to put two resistors. And then I'm going to come over here and put two resistors. Here's where we're going to apply our voltage. So let's say up here, we're going to apply plus 10 volts. And down here, we'll just use this as a common. And I'm going to take my output right here. So right now I'm going to put a voltmeter right here. So this circuit right here is the same way. That's the exact same circuit. So V out is between so let's say, just for calculation purposes, let's make them all the same size. So let's make this a 10K, let's make this a 10K, that makes this a 10K, that makes this a 10K. Since they're all the same size, that means they're going to drop the same voltage. According to Kirchhoff's voltage law, the sums of the voltage drops have to equal to the applied voltage. So it means right here I would have plus 5 volts, and right here I'd have plus 5 volts. What would my meter read? My meter would read 0. That's exactly right. Because meters read the difference of potential. Everybody okay? So we call this a balanced bridge. So what is this down here? And it's the ratio. So I could come up here and erase. So I can make this a 10K. And I can make this a 5K. And over here, I can make this I can make this a 1K, and I can make this a 500 ohms. So the voltage is set across 5K. So this would be whatever's on 5K. So I'd come over here and I'd say, okay, then my voltage, so if we call this R1, R2, we call this R3, and we call this R4, and VR2 would be equal to the ratio, the resistor I want the voltage drop across, 5K, divided by total, 15K, times the applied voltage. Did y'all learn that formula? We call it the voltage converter. Yeah, this is very important. It saves the calculation. First of all, the K cancels. So it's on the top and the bottom, right? You understand that in algebra. So K cancels. So this guy right here, VR2, is going to drop 1/3 of the voltage. So I just went ahead and rounded the fraction, right? I'm sorry, someone, yeah. So what would the voltage drop be there? Is that right? 5.1. 3.3 volts. Now over here, I have, so VR4 would be equal to 1K divided by 1.5K. So the ratio's wrong. What did I do wrong there? Resistor, we want the voltage drop across. So VR4 would be equal to 500 divided by 1.5K. That's 10. So what does that give us? If it don't give us 3.3, then I've done something wrong. So what we're saying is, if the ratio over here matches the ratio over there, then the bridge is balanced. Y'all understand? Balance means we have 0 volts, and we have 0 volts between those two points. And all it is just the ratio. The ratio is. Y'all understand? So what I can do, are we okay so far? And this voltage divider formula, that saves you, and it varies, it shows you right off the bat. If I've got this ratio of resistors, so what did y'all do in DC if I had a series circuit and I came over here and I said I had a 10K and then I said I had a 5K and then this is common, and then I had 10 volts applied. Well, you'd go through there, you'd add them together, you would divide that into 10 volts, you would get the current, and then you would multiply them. Well, see, this guy right here drops 1/3 of the voltage, period. So what you would do now, if I said, okay, let's raise this to 20 volts, what do you do in DC? You calculated the current, you took RT, you multiplied it by, right, you took RT, you divided it by 20, you came up with the current, and then you multiplied by 3. This guy right here will always drop 1/3 of the voltage, no matter what voltage you put on there. So that's what's so powerful about the voltage divider formula, is that if you change voltages, you just use the same ratio, no matter what the voltage is applied. So back in DC, that was something they should have taught that, but they might not. And we're going to use this formula here a lot, especially when we get into bipolar transistors and we're trying to calculate these voltages. Yeah, well, what we will do, and so that's what we do, is I take my thermistor. Yeah, what it was, it takes a device that changes a resistance when what it senses. So what I could do is I could come over here now and change this over to my thermistor. And it's like, what was it? It's like a 100K, 108K. So I could come over here and I could come over here and put my thermistor right there. And then over here, I would use a rheostat. And if this right here was 100K maximum, then over here I would probably use twice that, and I would use a pot over here that was 200K. This was probably a pot wired to the rheostat. And what I would do is I would set my thermistor at what I wanted to set 0 reference from. So if I wanted to be 0 at freezing, then I would take my thermistor and I would stick it in a glass of ice water with ice that floated in it. And then I would adjust that 200K until my meter read 0. And from then on, I have a reference of what 0 means, right? You understand? So I could put it at exactly 70 degrees, and then I could adjust it to measure 0. So now 0 would equal to what? 70 degrees. If the voltage started going negative, it means it was going below my 0 reference. If it started going positive, it would go toward my 0 reference. So now we can set, so over on this circuit right here, over on the, I just think it's good. So over on this circuit right here, I might put my thermistor right there. And then I might put a fixed resistor down here. And I might put 10 volts, and I come over here and I read plus 5 volts. Well, what does plus 5 volts mean? It really means nothing, right? You understand? But what I can do with a Wheatstone bridge is I can set what 0 means, or what voltage means. So I could set this thing, I could come over here and adjust I could put this at 70, I could put this right here at 70 degrees. And then I could adjust this, and if I wanted 5 volts at 70 degrees, then I could adjust this guy over here until it measures 5 volts.
I want to try to take it back. You said one time, thermostat in height, right? And you actually start to change and make sure that you kind of visualize that function. You connect it to the pot and then start to connect it.
No, you connect this circuit over here. So I would come over here, and my thermistor has leads coming on. So I would take it, and then I would come over here, and I would take it and put it in a glass of ice water with ice floating around in it, right? And this would give us pretty close to 0 degrees centigrade. Yeah. Or I could know 0 would actually equal to 32. It's up to you and your instrument, right? And then I would adjust this until my meter measured 0, or until I got an output out of there. Now, if it goes up, then I would set it up so when it goes up, my voltage goes up, and when it goes down, it would go negative. And so that way that voltage is going to mean something, right? So any sensor that we got where I need to set a reference, if I need to set a reference for this sensor, then what that means is what? That I'll have to use a Wheatstone. If I don't need a reference, if I just use a voltage, I don't care if it's 5 volts or 10 volts, if I just say, okay, I want this thing to switch at a certain temperature, then we wouldn't use a Wheatstone.
So that you have in that cup there, once it goes too high or too low for the constant to set down or cut off or.
Well, that wouldn't be with this. That would be the circuit that we feed this into. So on my thermostat, I got a thermistor in it, and I don't know if I've got it over here or not, but you can literally see the thermistor in the back of the old digital thermostat that I took off my house. So now I got one that's real, you got one now where you can set it at 75 degrees, or you can set it at a certain temperature, and it'll automatically switch your heat on or cold on or whatever you need to keep that temperature. Like I said, I don't really like that because so mine, I can switch mine between heat and cold. So if I've got it on cool, it's going to maintain a set of temperatures that I program into it. If I put it on heat, it's got another set of temperatures that I program. Does that make sense? Yeah, so these digital thermostats are really neat. So mine, I can set 4 temperatures during the day. And you got vacation. So if you're going on vacation and you got your air conditioner rolling on, you could set that vacation to 82 degrees. You flip it on there. And then you can program when it goes, then you can say like, if you go on Friday, you say, well, I want to turn my air conditioner, I'm coming back on Wednesday. Well, you turn your air conditioner back on Tuesday. And if your house is cool when you get in there, but you're chilled. So these digital thermostats are really interesting now that we can do. But basically, if you looked at the sensing element on these things, these are going to be some mysteries. But how did they do it? They had to set what these temperatures mean. There's nothing that's supposed to be fixed. What? This? That's just seed wave. I do need to unplug that so I don't accidentally grab it. I've been known to do that before. Yeah, what you're doing is you're seeing the heat come off of it. Yeah. So you're seeing the heat come off and it's messing up the light. Well, I can see it from my angle. Yeah. Oh yeah, I do. Yeah. That's pretty cool. So everybody okay with the Wheatstone Bridge? It's real neat. So any type of device that I need that changes its resistance, and I want to get a voltage out of the circuit, right? You understand that? And I need to be able to set a zero reference or a reference, then we'll use the Wheatstone Bridge. So this is another one. This is a photoresistor. And I do have some of these up here. I've got enough to hand out for everybody. So if you got your own meter, you can play around with it. So this is photoresistor. So you can actually see the semiconductor running through there. And of course, when we expose this to light, then these guys, they always opt. I'm going to put my meter across it again. These guys have revolutionized our lighting systems now. So I've got mine on. So right now, mine is measuring. Let me change my angle of my meter. Okay. So this guy here is measuring 712 ohms. And I'm just going to come over here and just so on these, as the light goes down, the resistance goes up. The light goes up, resistance goes down. So this is actually using the energy from the photons that's striking it to change the resistance of the semiconductor. Where do y'all see these at? Every light that comes on at dusk and every light that goes off at dusk and comes on at dawn uses this as a sensor. So used to, when I first I worked at a grocery store and, we had timers on our lights in the parking lot. And what would happen is you had to do it. You had to change it often, right? Especially sometimes. You could see people that didn't change it because you'd be driving in the summertime, when we was on daylight savings, the parking lights would be on. Because they didn't do what? They didn't change their time. So now all these lights on the interstate, I've got motion detectors on my house. They don't come on during the day. They only come on at night. They only sense motion at night. You got lights that come on at night and stay on. We go off during the day. These are the sensors of you.
Does it conduct or balance out, I guess, but my meter's like jumping around or something. Wondering, if you come on my end.
Well, first of all, mine is clipped on there, so mine are stationary. When you touch them with your lead, it's very, very important. And plus, on these guys, if you accidentally touch both your leads at the same time, this is not light. This is me. So it's putting me in parallel with mine, and that means if I vary my touch just a little bit, it's going to move around. So, And then plus you're trying to cover it with, so it's better, what I'm saying, Janice, it's better to use clips on this instead of trying to hold. Because notice now I got my hands free, and I can do what? I can cover it and actually see it sense and light. Is that? Of course, if I wanted this light to mean something, then we have to take this and convert it into a voltage. So that means I could do the same circuit. And these are, by the way, these are the symbols I was looking at a while ago. These are all the symbols we have for this photoresistor. This is what most people call photo cells. So commercially, we call these photo cells. Technically, they're photoresistors. That's their actual name. So y'all have heard of photo cells before, right? So that's what commercially we call. So these are going to be rated in a tolerance. They're going to be rated in a wattage. So the bigger they are, the more wattage they could run. But we'll find out later on. We have some amplifying devices where we can take this output and amplify it quite a bit. And this is where the Wheatstone bridge actually came into play. Another device, this is over here somewhere. Most of the time we use this with a device, and it's very complex inside, but it's real easy to work with. And unfortunately, we don't have time to really teach them in detail and all the features of these. And these are called operational amplifiers. Most people just call them op amps. And the symbol for them is we draw a triangle on its side. And then we have two leads called plus and minus. The plus symbol means non-inverted. So these are symbols, and we use a symbol to represent things, right? Math, we use a symbol to indicate plus, to addition. But you'll run into these symbols often, and that's what you got to figure out. So if that's non-inverted, then this input right here means what? So one of the main uses we use this is for something we call a comparator. This guy here has all kind of uses. And I'm going to jump over, even though we're really not supposed to do that. It's not going to be on any test by the way. But op amps are really, really neat. And what's nice about it is you can set the gain on them without doing much math. You can use them as what we call comparators. So let's say I set this right here to plus 3 volts using my rheostat. Then what happens, as long as this voltage is less than that one, so let's say it's setting at plus 2, then my output would be 0 volts. As soon as this thing gets up to 3 volts, if I set that to 3 volts, as soon as it gets up to plus 3.01 or 3.1, then the output would switch to whatever you power it to. So let's say plus 5 volts. So what we have to do with this, when we call it a comparator, is looking at an unknown and comparing it to a known. Op amps, there's a lot of books out there on that. We can set these things up as amplifiers and calculate the gain. When we get into bipolar transistors, it's complicated to calculate your gains and stuff like that. But this guy right here, very, very simple. No. But what you're going to see is most sensors, most digital sensors are either going to be true or false. But what we like to do is we like to set what we call a threshold. Well, this right here is a little circuit where I can set the threshold. So what happens, it means I can put 3 volts on there. As soon as I get the output of my sensor, if it gets above 3 volts, the thing switches. If it's below 3 volts, and we'll show y'all this when we go over the manufacturing line. A lot of our light sensors and stuff like that has a place that we can set a threshold. But all you're basically doing is reversing the threshold. Or change that value right there. So you do this, anybody got light sensors on their house? They come on at night? Or even motion detectors. You got a little thing on the bottom, you can do what? You're setting the threshold. Basically, you're saying 5 feet, 6 feet. It don't give you infinite. You have different switches. So basically, all you're doing down on this guy is just switching 3 resistors in there. And so you can actually set the distance and you can set the range, like night and day, how dark you want it to be. Most of them have two adjustments on them that you can do. Photovoltaic cells. Most people call these solar cells, commercially. So y'all need to sanitize these. So I'll put these, we can use these up here and give them back. Well, these are real small. That's going to be small. Technically, these are called photovoltaic cells. Most people refer to these as solar cells. Some people, when they live out in the sticks, like have these on their house. The highway department uses these things a lot when they're trying to put signs way out in nowhere where they don't have electric power. You'll see it on the side of the road. They have a solar cell up there. Huh? Not that I know of. It's your home. Sometimes they charge you if you have them on your home, but they can't make it illegal to put it on your home. So, especially in the United States, they may do that overseas. So these, so technically this is a symbol. This would be a symbol for one cell. And then what we do, I think these guys here, what we'll do is, I probably need to, get a brighter light. I might use, the light off my, phone. So I'm going to take my meter now and I'm going to switch it instead of having it on ohms, I'm going to switch it to volts. DC, this is DC volt. And that's something very, very important that you got to pay attention to on your meter, right? So that's happened a couple of times in this class where you don't measure something and I come back and you're looking at a DC circuit and you got your meter on AC. What's that? That's just the part number. This is 0.5 volts, and I don't know what the 250 stands for. That's a good point. So right now, mine is putting out 260 70 so millivolts. Of course, this is varying with light. So this is putting out volts. And of course now if I come up here and cover it out, my voltage goes down. And I take it off, my voltage goes up. And then of course, the brighter the light, the more voltage it puts out. We had one of these. I'm not going to tell you who because y'all. But we were donated one. I think Alabama Power donated a solar panel, and it was pretty big. And we had it over in A200, and we had it on fluorescent light, and we had a light emitting diode on it. And it was anytime you turned the light on, the light emitting diode. And well, one of our instructors decided they were going to take it outside. And as soon as they got outside, it blew the LED. So that solar panel's not working anymore. And then of course, they blew the LED out. So these guys right here are pretty neat, and we run into these all, so they sense light, but they don't have to be powered, right, to understand. So, photoresistors, you have to power those, right? So most light sensors, you have to provide them, power them, but this guy right here provides his own power. We can take them and we can hook them in series. So when we hook DC sources in series, what does that increase? So when you hook them in series, what does that increase? It increases the voltage. Right. Yeah, it's just like resistors. So the sums of the voltage drops in a series circuit equals to the applied voltage. So that means if this is 5 volts, and this is 5 volts, and this is 5 volts, and this is 5 volts, if I measured across here, I would measure 20 volts. Current would be the constant. So if this cell was rated at 100 milliamps, this guy was rated at 100 milliamps, this guy was rated at 100 milliamps, this guy was rated at 100 milliamps, then I would get 100 milliamps out. Period. If I hook them in parallel, then the voltage is constant, but what happens is the current's added. So if I came over here and this was plus 5 volts, and this was plus 5 volts, and this was plus 5 volts, they'd have to be the same, right? You understand that? And then I came over here and this was 100 milliamps, this was 100 milliamps, this was 100 milliamps, then I could get 300 milliamps out of this one. So this is what they do. So this is why solar panels are so big, because they got thousands of little old solar cells, right? And they're hooking them in series to get the voltage up, and they hook them in parallel to get the current up. And this is exactly what's going on in your car. So your car has 6 cells in it. Each one of them puts out 2 volts. They're hooked in series. But if you ever take a battery apart, you see it's got plates like this, and then they're connected together, and then it's got a space, and then it's got another plate. These are hooked in parallel, and then these are hooked in series. So you got a bunch of plates cells that make up each side. They're hooked in parallel. Then you take six of them and hook them in series, and you get 12 volts at a certain amount of current, depending on how many plates they can hook in parallel. So this is why most batteries, the more current you get, they're what? They're bigger, because they got to hook more plates in parallel. So Yeah, so the solar cell, the amount of light you're getting out of the solar cell wouldn't be light enough to provide the energy to convert it into the voltage. And I've had people that try to argue that. And so if you see something on YouTube that makes the laws of physics wrong, then that's impossible. Like I said, I was telling my other classes, and I said, okay, there's a thing up there where a guy's got a generator, got a motor, and the motor's feeding the generator. He plugs in the motor, gets the motor up to speed, then he unplugs it, and he takes the output of the generator to feed the motor, and the thing just sits there and runs. That's impossible. Because if it takes 100 watts, if it takes if I need 100 watts of energy over here, this guy's probably gonna require 150 to run the motor. So nothing's perfect, right? You understand that? So we'll never get more out than we put in. Never. No, it just started. The motor would stop. We had a guy come in. He says, "Man, I got a great idea. We got all these DC powered forklifts in our plant." He said, "What I'm gonna do is I'm gonna get a generator and I'm gonna put it on the wheels, and when the forklift runs, it'll charge the battery." And I tell him the batteries are gonna run down faster because the power you get out is gonna be less than the power you put in. So, but yeah, we had a guy that thought he could use a piston engine, and on the upstroke, when the piston engine came up, he could use that to generate the actual motion. So he thought the motor would move by itself. So yeah, we never get more out than we put in. So and I told you about the guy that interviewed for the job, right? And he talked about transformers getting power gain. He says transformers either step the power up or step the power down. And what's the problem? Power is work. So power out. So power in. So workout. Let me see. Workout equals to working and times efficiency. And efficiency is always less than 1. So unfortunately, it always takes more work that we put in than we actually get out. So since power, and we talked about this, so since power, so technically if you turn on a 100-watt light bulb, then what is our power company got to give us? We say 100 watts, but actually it's probably going to be like 110 or 150 watts, depending on how far you're out. So solar panels, these guys are really nice. The technical name for each one of them is a photovoltaic cell, but most people call these solar cells. So I could use this voltage to do what? To measure the intensity of light. Hall effect. This book talks about Hall effect. Varies a voltage proportional to the strength of the magnetic field. Must be powered by external sources. 2 types. We have what we call a lashing and an analog. I got the circuit set up somewhere. Unfortunately, I'm out of Hall effect, so I need to find that circuit. We use these for when we talk about sensors, we have what we call proximity sensors. And anybody know what that means?
No. From that spot right there,
Well, proximity. When we talk about technically, proximity is when something's in a location, right? Does that make sense? So we use proximity sensors to sense when something is at a precise location or a precise distance. Over time, so the first proximity sensor that they ever used was a device called a limit switch. And I don't know if I've got any limit switches over here, but we can see them over there. And what would happen is when so the limit switch would be a big old thing, and then it would have an operator coming out of it like this, and then we would run wires into it, and whatever would happen when it would come up here and it would hit the operator, it would close contacts or open contacts. So what it was doing, it was sensing when something was at a certain spot. So these are proximity. These became known as the limit switch. So the first, so technically when computers first came out, the operating system was built into the computer. And you had no option but to use that. You couldn't upgrade it. You couldn't do anything like that. So eventually they came out with these things called disk drives where we could actually store an operating system onto a disk. And these became known as disk operating systems. And they used this as an acronym, so we called it DOS. This guy was text-based. You had to learn a bunch of commands. So when you booted your computer, this is what you saw. Your whole screen was this. And by the way, this is still a viable, a viable shell. If I get it to load. We call it command prompt. Come on, please. Yeah. So this is what we saw. This is what we saw when we turned our computers on and it booted into DOS right here. We saw this thing. That little flashing line, we call it the cursor, because everybody cursed at it, I guess. And what you had to do, you had to learn all these commands. So you'd have to come up here, like CLS with squeal screen, you could look at the directory on your computer, you could do a lot of things, but this was the whole screen. This was the whole screen. And this was an operating system called DOS. We still use it a lot. If you ever get into network, we still use this a lot. So one of the ways we send information over an Ethernet network is something called TCP/IP. I don't know if you've heard of that before. Well, this is where you can control TCP or the TCP protocol. So I can find computers, I can trace routes, I can set IP addresses, I can do all this neat stuff with this. So this is the only reason why it's still available. And this was DOS. This was the first disk operating system that we had. Yeah, that's what. And this is what I don't know if you heard what Cameron said, but you have to learn the syntax. Not only do you have to learn the commands, you have to learn the syntax of the command, the correct way you write it. So you make one mistake, you could cause problems. We had a, and they took it away from us. There was a DOS prompt command. It might still be on this one. No, it's not. We lost it on the. It's called debug. Debug, you can do anything on it. In fact, the error messages that pop up when you do certain things, we figured out how to change them. So you literally pop up, and that was back in the old days that we would do things that wasn't right. But anyway, like if they did something wrong, we said, that's the wrong command, stupid, and stuff like that. That would pop up instead of the real. So debug was dangerous. So that's one of the reasons that when they came out with Windows 7, they did away with debug. But Windows XP still has it in there, by the way, if you play around with it. So this was DOS. Well, when they came out with Windows, well, Windows is a disk operating system. But everybody learned DOS was this cryptic text-based operating system. So we started, instead of, so given these disk operating systems, we started to give them other names besides DOS. So the first proximity switch was a limit switch. And they're still used. Very simple, very cheap. They're fairly durable, but the problem is they're electromechanical devices. So if people don't treat them right, they will fail. So the next proximity sensor, so now when we talk about a proximity sensor, these are going to be what we call non-contact sensors. So the limit switch is a sensor reach. So the limit switch is a contact sensor. It's got to make what? It's got to make physical contact. So now if we use the term even though a limit switch is a proximity sensor, we call it a limit switch. And then all of your proximity sensors are going to be non-contact. So the photovoltaic cell, this is not a proximity sensor. This is not going to sense where something's at. This is going to give us a range for voltages, right? Does that make sense? And this is an analog sensor. So Hall effect. We have two types. We have an analog. So the analog sensor would give us we need to take a break. So an analog would give us a voltage proportional to the magnetic field. So we use this a lot. So we know, and these can be proximity sensors. They don't have to make physical contact. So now, most meters, these meters don't have it, but now most meters, you have an indicator that you can come up and you can sense where electricity is flowing within your wall. You just bring it up there and a light will come on. Well, that's usually what? That's usually a Hall effect, and it's doing what? It's sensing the strength it's just sensing a field. But these guys, this is what they do. They sense a magnetic field. Let's take a break and let me see if I can find my hole. They're going to have to be powered up. These are electronic. And basically what these do is they sense the strength of a magnetic field. We've got these all over the line over there. What they do is, what they do now so what they do now, especially under pneumatics, is that a lot of times on pneumatics, they want to sense the position of a piston or a cylinder. These guys are here. So in the old days, if we wanted to, in using hydraulics, we can't use these. Usually they use limit switches, and what they'll do is they'll have limit switches mounted on the actual. So this is a unit we found when we were looking through some stuff. So these are what we call hydraulic. These are pneumatic cylinders. So what we do is we put pressure in one side, and then it's got a piston here that pushes it this way, and then we exhaust on this side, and then we switch it with a solenoid control valve to actually switch this. But what I wanted you to see is these are little limit switches. These are electronic duty limit switches. So technically they're proximity, but we don't call them proximity sensors. We call them limit switches. They have the honor of having that name. So when this piston comes out and extends, it's hard to do. Then what it does, it physically strikes these limit switches. And then we can bring that into our control circuit and make decisions on what happens when it strikes that. So this is good. I wish I'd had this. So these are limit switches. And so we got, on this one, they just got this ball on the end of the piston, but we'd actually make that thing strike these limit switches when it moved, when it was actually doing the work. Pneumatics. We still have to do this kind of stuff on hydraulics, because hydraulics, the cylinders themselves have to be made out of a hard metal, like steel. What's nice about hydraulics is we don't run those at extremely high pressures. So a lot of your cylinders are either plastic, or they're aluminum. And what's nice about aluminum is aluminum does not concentrate a magnetic field. So a magnetic field passes through the aluminum. So what we do now is they take the pneumatic cylinders, and you can buy them this way, and they literally put a magnet on the piston. And then what we can do is we can take these Hall effect sensors and we can strap them onto the side, and now we can sense the position of the cylinder or the position of the piston or the rod without actually having it strike limit. So this is extremely popular now with pneumatics. Still can't do it with hydraulics, so we'll use devices called linear LVDTs, linear voltage differential transformers, that actually gives us an analog output it looks like a piston. We use those, or we use limit switches if we have to know the position of the actual rod itself. So this is just a typical compatible magnetic piston, and it's actually got a watt on it. It's got a magnet. So what I can do with these Hall effects is I can literally come up here and just strap them onto the side. So it's usually got some way we can do that. And then we can just strap these Hall effects onto the side, and now we can tell if the cylinder's fully extended or retracted. And these are all on all our manufacturing lines over there. This is what it means. And then we can take this. But these are digital, which means they're these are digital Hall effects, which means what? They either turn on or turn off. And I was going to. And then we have analog ones that basically actually measure the strength of the field. So we have these devices called clamp-on ammeters. So they have these clamps on them, or they have a tube, and then they are spring-loaded, and we can come over here and we can put a wire through the center. And literally, we call them ammeters, but they're not actually measuring current. You know what they're measuring? When current through a conductor goes up, the magnetic field around it goes up. So these devices are not measuring current. They're measuring the strength of the magnetic field that produces that current. To induce it though, to induce it in this thing, so this is just, we call these CTs or current transformers. We have to have a magnetic field. We've already talked about this, right? We got to have a conductor. And then we got to have motion between the conductor and the magnetic field. And what determines the amount? The strength of the magnetic field the number of conductor loops, and then the speed of the motion. So this is the way your alternator's running. It's spinning an electromagnet around a bunch of stators. I don't remember how many phases it is. It's more than 3 phases. And so how do we regulate? How does your voltage regulator on your car work? Well, it changes the watt, the strength of the magnetic field. So that's what your regulator's doing, which causes your alternator to put out basically the same voltage all the time. So if this thing right here's got to work, If I'm going to induce a voltage into this, then of course the big thing we have to have is motion. So these guys only work with AC. They'll only measure AC. The clamp on will only measure AC. Unless it's got a Hall effect in there. So a lot of times they'll put a Hall effect in here, and then it measures DC. So if you got a clamp on ammeter that measures both AC and DC, it's going to cost you a lot of money, and it does a Hall effect. Because this guy only measures AC, right? That makes sense? So that's what we're doing. We use these things all the time to sense magnetic field. So let me get back to my PowerPoint, the actual PowerPoint that goes with this class, right there. So odds are, we got these things in our car. They don't usually use these, but they got a thing that senses this, that actually works your anti-lock brakes. So, but it's not exactly a Hall effect. We have these basically that sense the speed of your car. Used to, in the old cars, if you got a real old car, you would, if you pulled off the speedometer, you see it had a metal cable coming into the back, and it was actually spinning off the transmission. And it had a set of magnets working against the spring, and the magnets would spin, and it would cause the thing to deflect depending on the speed. Now, if you open up your panel and you pull off your speedometer, it's going to have two wires coming up. So how does it know the speed? Well, it's got one of these in your transmission, and you got a chunk of magnet on one of your gears, right? And every time that thing spins around, it does what? It generates pulses, and they use that to generate. So we use these things to sense speed. We use these things to sense positions. We use them to sense a lot. Of course, the main place that we're using them on our manufacturing line over there is to sense the position of the piston, of the rods on the piston. So these guys are going to be at least these are going to be at least 3 wire sensors because we have 2 columns. So most of the time these things will have 3 pins coming out of it. That's why I wish I could show it to you. So a lot of people think these things sense metal, but they don't sense metal. They sense the strength of a magnetic field. So this is showing you one example. So you might have a Hall effect sensor, and inside the Hall effect sensor, it's got a permanent magnet in there. And what happens is when this thing flies around, this is metal, and then when it comes around, it concentrates the field and causes the output of the Hall effect to change. This is another example. So I have a magnetic field, and then what? Then this steel ball rolls across. It's not sensing the steel ball, it's sensing when the steel ball comes back and it concentrates the magnetic field. So Hall effects do not detect metal. The Hall effects themselves sense the strength of a magnetic field. Ultrasonics. Everybody familiar with these? Converts the ultrasonic waves into electrical signals or vice versa. Measures the time interval between the sending and receiving of an echo. So these guys are definitely electronic. They're not standalone. So ultrasonic. So what it does, it sends out pulses or sound waves, then it calculates the amount of time it takes for it to come back, and then it can use that to sense. So what can we sense of these guys? Do I have that? Sense distance, we can sense motion or movement, levels, speeds, or direction. So ultrasonics. So anybody ever run into these? Some examples. Right, the robots. You're taking intro to robots. I mean, y'all competing those robots now. You won any yet?
Well, we don't know.
Oh, okay. Oh, yeah. The way that thing is set up is it's good for social distancing because you don't have to do it at the same time. But ultrasonic sensors, so that's sensing distance, right? We got cars now that have automatically hit your brakes when you're at a certain speed. I've got my wife's van's got the ultrasonic sensors on the back. When she's backing up, if she gets close to something, it beeps it and lets her know it's there. When people's driving beside her, she's got an orange light that comes up on her mirror saying that there's somebody beside you, even though it's out of the visual plane of the mirror. We use, huh? Yeah, the blind spot, that most things have. We use these on our cars a lot now. Over in the manufacturer line, we're using these to detect the size of an item when it moves by. So on ours, we're actually using these to sense distance, but we translate that into a size. Does that make sense? Ultrasonics, we use those, when they can actually look through your skin with these things. Yeah. Ultrasonic one. There's some ultrasonics. Our mobile robot uses these guys right here, which it stopped working a long time ago. That's probably one of the oldest robots that we have. Is you go in there, we call it a He-Robot. Of course, they spelled it he, put a dash in there and called it robot. And that gave us problems with a lot of ladies because they said the robot was sexist. So we called it a He-Robot. Look at that. Piezo, by the way, piezo means it senses pressure. Piezo resistive means it changes its resistance with pressure. The only, so a lot of our pressure sensors are just piezo resistive. That means they can receive real calls. Are we okay? Piezo resistive. We have what we call a piezoelectric. Piezoelectric. You ever run into those? Anybody got a little cigarette lighter you can click that don't have the flint in there? And it generates that spark. That's a piezoelectric crystal that it's striking. Which is pretty cool. Pressure switches. I have one of these somewhere, but like I said, I think most of them's over in the other lab. Light emitting diodes. Everybody okay with light emitting diodes? Y'all know how those work? LED. So we have transducers, photoelectric. This is chapter 15, but I think this is chapter 15 in the book. I'm not sure. Light emitting diodes, liquid crystal, photodiodes, photoresistors, photocells, and this is why we jump up here. Is that chapter 15? Photoelectric sensors, or is it still in chapter 8? I might need to correct it. Yeah, where's it cover photoelectric devices at? They call it photonics. Now, what we're doing is some of the sensors that we have are actually photo sensors. They sense light. So yeah, so first thing we need to figure out is how a light emitting diode works. We'll also look at liquid crystal, photodiodes, photoresistors, and photocells, photovoltaic cells, which we've already looked at. So we're okay here. And then we'll look at these different types of photoelectric cells. We already looked at photoresistors. And this is just nice to know stuff. This is nice to know stuff. This is nice to know stuff. By the way, most of the time light moves at such a high frequency that basically what we do is we measure, so we're looking at this moving through an object. So this is kind of like waves coming in off the ocean, and there'd be space in between them. So what we're talking about is we're talking about the spacing between the waves. So if this is moving through a conductor, then we know from here to here just from here to here would take a certain amount of time, but also it actually has a length of time, a length that it's actually on the conductor. This is what we refer to as the wave. So when we start looking at light and it's moving through the air, then that means these guys actually have a length that we refer to as wavelength. So these are some of the wavelengths that we look at. So 660 nanometers through 850 nanometers, these wavelengths would be visible to the human eye. Anything outside that would be invisible to the human eye. It's still there, but you can't see it anymore. So we call them infrared, ultraviolet. So these would be wavelengths that you can't see. So sometimes when you're looking at a photo sensor and you don't see a light, it doesn't mean it's bad. It just might be what? It might be at a wavelength that you can't see. And this happens quite often. Every frequency, high frequency, are usually given in wavelengths instead of hertz. Every repetitive electromagnetic wave moving through a media has a length referred to as a wavelength. The wavelength is determined by the frequency of the wave relative to the speed of light, which is 3.3 times 10 to the 18th meters per second. So wavelengths are given in meters. They're not given in the English standard. Wavelength for after light is given in nanometers. So this is the formula. Do you need to know that? No. These are the frequency spectrums, what we refer to. You've heard of UHF and LF, those different frequencies. Well, this actually gives this chart right here, and you can find this on the internet. This gives you the different frequencies that fall into these categories. So ELF, which is extremely low frequency. So the lower the frequency, the better it is to pass through stuff. The higher the frequency, it's going to start bouncing off stuff. Does that make sense? So, in fact, we ran into this on submarines trying to transmit while they're underwater. Well, they tried to use, if they used high frequency radio waves, it wouldn't go anywhere because they were trying to transmit it through water. So submarines transmit using what they call an ELF transmitter. So this is our visible spectrum right here. So we have ELF, VF, VLF, LF, MF, HF, VHF, UHF. These used to be our TV channels right here. Yeah. So VLF is very high frequency. ULF is ultra high frequency. So this was back in the old days when we had TVs. They came out with the UHF channels. So that's what it was. That was the ultra high frequency channel. And then this is the visible right here. And then we get into X-rays, cosmic rays. When we get into ultraviolet, these wavelengths right here start getting dangerous, right? We had when we was over in Japan, we lived, I guess it was about, our barracks was like, maybe, oh good gracious, probably around 800 feet off the runway. and we'd be listening to our stereo. You could tell when the plane was fixing to land. It'd have its radar on. It was our stereo would start going zzz, zzz, when it was sending out the pulses. So I've got a bunch of recordings out there that's got buzzes like that. Brings back memories. So we okay on engineer notation, right? Kilohertz, megahertz, gigahertz, terahertz, petahertz, and exahertz. And this is not going to be on test. A lot of me now though, when holes and electrons combine, so I should have jumped to right here. When holes, that other stuff is just nice to know stuff. When holes and electrons combine at the junction of a forward bias diode, energy is released in the form of photons. Silicon and germanium release very few photons, and these semiconductors impede the release of the photons. So even if you got a glass diode, you can't see the photons coming off that. For this reason, light-emitting diodes are made from doped gallium. So that's the semiconductor. So basically what we do is we expose the junction. We use gallium, and then we dope it with other elements to determine the color. We got a chart in here that shows you what its dope is. So the photons they release, these have to be forward biased. So it's basically, the symbol is about the same. So we start off with the symbol of a regular diode. And then we usually put two arrows coming out of it, indicating it's a light emitting diode. So what happens when I forward bias it, when I make the cathode positive in respect to, when I make the cathode negative in respect to the anode, and we exceed the VF, so some of y'all run into that on your diode lab. So you're down at 4.45 volts. And when you measure it across here, you measure 0 volts when you have 0.45 volts on your diode, because the diode was acting like an open switch. So that means this LED will not come on until we exceed the VF of the diode. Anybody know the VF of an LED? It's approximately 2 volts. So these guys are not designed to be rectifiers, because they're going to drop 2 volts, right? You understand? Around 2 volts. These guys are not designed to be rectifiers. They're designed to emit a light. They're designed to be indicators. If you reverse bias them, so if you forward bias them, the LED comes on. If you reverse bias them, the LED cuts off. And you can reverse bias them until you exceed the PIV rating of the diode, and then it'll mess it up. If it's what we call a radial type, where the two leads come out one side. Yeah, so it's if you got the radial type LED, it's got the hump on it, and then you'll notice one side will be longer than the other, and this will identify the cathode, and this guy right here will identify the anode. They also, if you look at it from the top, it's got a little ring going around it, and then one side of the ring will have a flat spot on it. And if you'll look, that aligns with the cathode also. So they give you two methods, so if you cut it off. And some meters can actually check this, and y'all saw this when y'all did your lab. Some meters, you can actually measure that VL. If your meter puts out over 3 volts, when you got it on the diode scale, then it will turn the LED on. But your meter don't pull out enough current to cause the LED to really glow real bright. You got to really, really look at it. These guys produce their maximum light. So rule of thumb is 2 volts VF and around 15 milliamps to get it to glow real bright. So that means if you put, 2 volts at 1 milliamp through there, it's going to be on, but it's going to be really, really dim. So once you get it, then the amount of light it does would be determined by the current load. But that's what we do for rule of thumb. We need that. If we don't have it, then if we got it available, then we need to look it up on the data sheet. Contrary to popular belief, the color of the lens of an LED does not determine the color of the light emitted by the LED. The light only enhances the color of the light emitted by the P junction. The color emitted by the LED is determined by what we dope it with. Well, okay, that makes sense. So a lot of people, and you've seen these, I've seen LEDs that's got clear lenses on them, yet they'll be red. But it don't look as bright as it does if you put it inside a red lens. Doping versus color. Gallium arsenide creates light in the 900 nanometer infrared range. Gallium arsenide phosphate, 600 nanometers, red light. Gallium phosphate, in 500 nanometers, which is green. So gallium nitrogen, 430 nanometers, which would be blue. Gallium arsenide phosphate, 365 nanometers, which would be orange. And then we have that one that has yellow. For years, we only had 3 colors. We had yellow, red, and green. For years. Then they came out with a method. The guy that invented the white LED actually won the Nobel Prize for Physics. So that you think about an LED that's producing more than one color. So these are actually the doping in the color that we get. Here's the VL. So here's the VL. So this is the infrared. So this guy right here, this is actually a part number, by the way. This would be 1.5 volts, 1.7 volts, 1.8, 1.2, 2.2. So notice this 2 is the watt. It's not a fixed value. It's actually, but it's good enough for calculation. So these are different colors. And now we got up to white, pale white. And this is amazing what they do with these things now. The intensity and the power they get out of, the lumens that we can get out of LEDs are really something now. I think even Bryant-Denny Stadium has changed over to LED lights on their, and they can actually change the color on them. So used to, when they had those hydrogen lights up there, if they ever turned the lights off, it took like 15 minutes for them to cover them to, it took a long time for them to do what? Come on. Now with LEDs, they can turn them off and on with no problem. So here's the LED. Everybody okay? Normally we don't draw the circle around it. And we run into these things all over the place. We don't use them in our TVs anymore, but these big old boards, these are light emitting diodes. That we see on the side of the road. These are light emitting diodes. These are called 7-segment displays. And I do have a lot of these. It's called a 7-segment display. I'm going to see how sanitizer. And so 7 segments. You count the segments. 1, 2, 3, 4, 5, 6, 7. We can just play any number with these, right? And they name the segment. So the top segment, we call this A, this would be the B, C, D, E, F, and then the bar is the G segment. And normally so what we would do if you think about this, let's see if I got a, so if you think about this, you got an LED, then we got 7 of them, right? So there's 7 of them in there. And usually since they draw them so close, they don't actually use the true symbol for 1, 2, 3, 4, 5, 6, 7. Okay. And these are all LEDs, and then normally we have one more, and they identify this as the decimal point. It's not considered a segment. CT for decimal. So you can buy them with right-hand decimal points, you can buy them with left-hand decimal points, you can buy them with vertical decimal points. So that varies, but these up here stay the same, right? So what we do is that these things work the same way. So when I count the number of pins, so just this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So to bring out the 7 LEDs with the decimal point, then we're looking at what? 16 pins. Well, when you count the number of leads coming out of this thing, how many do you count? Mine's got 10 on it. Well, what happened to the other 6? So normally what they do is they'll come in here and they'll take these and connect them together. And then they'll take these and connect them together. And then they'll come out with 2 wires. And one of them comes out the left and one of them comes out the right. So you can use either one. In fact, these are actually connected together. So and this would be called a common cathode. And I could do the same thing. I'm not going to draw all of them, guys. So I could do the same thing, but over here, what I would do is I would take all the anodes and do what? Connect them together. And we call this, and then we have, this would be a common anode. So if I came over here and I was going to turn on an LED, and let's say I come over here and did this, and I came over and put a battery down here, and I'm putting in there reverse a DC voltage source. What would happen as soon as I turned it on? Let's say this is plus 5 volts. What would happen as soon as I turned it on? It would blow the LED. Yeah, it's not going to be almost a short circuit because this guy here is going to try to drop 2 volts, right? But it'll burn up just like that. Yeah, and so I'm putting 5 volts over here. This guy, as soon as I get above 2 volts, this guy turns on. As soon as it turns on, it acts like a closed switch. So anything above 2 volts would be considered a short circuit. So what does that mean if I'm going to do this? Somewhere down the line, we're going to have to put one of these guys, right? I'll put a resistor. So that resistor would drop the voltage. So if this is plus 5 volts and this is 2 volts, then I would size a resistor that would drop 3 volts at about probably around 10 milliamps. You never want to run these things wide open. So what we could do over on this, if I've got a common anode, what I would do is I would come over here and I would come over here and take this and I would go ahead and connect this to like plus 5 volts. And then what I would do is I'd have a resistor in series with each one of these. Now I could come over here and I could have came over here. And you'll see this done every once in a while too. So I got a battery charger and it's got LEDs on. It's got a 7-segment LED. So what I could do is I could come over here and put a resistor right there. And then we come over here, whatever segment I want turned on, I would just come over here. Let's say this is plus 5 volts. I could put a resistor right there. And then I could come over and I could turn on the segments just by connecting these common, right? Now what's the problem with this? Well, the problem with this is that the more LEDs you have on, the dimmer it gets. So if you're going to turn on one, it would be on real bright, so it varies with intensity. So if you've ever seen that, and this is what they use. So the preferred method is to put one resistor into each lead. So what we have is I'll see if I can find some of these. We have resistor pack, guys. We'll have an integrated circuit, and then it'll have 8 pins on this side. 1, 2, 3, 4, 5, 6, 7. I don't have them in front of me. And then it'll have 8 pins on this side. In between each pin is a resistor. So most of the time you don't actually see the series dropping resistor for the 7-segment display. It'll be an integrated circuit. We can see that, I think, on this function generator. We'll open it up. So common anodes, what we do on a common anode is we turn these on with a plus voltage. A common cathode, we turn these on with a common or a minus. So what do you got there? Once I hand, you have a common cathode or a common anode. We know for a fact there's 8 LEDs in there because they have a decimal point. So if we ran a wire, 2 wires to the cathode and anode, we know that it would require 16 pins. It only requires, it's only got 10, right? But is it common anode or common cathode? I say, I don't know. I don't know. But you probably look on there, it's got a watt on there somewhere. It's got a part number on there, right? Can you see a part number on there? Yeah, so what we would do if I didn't know, I would just go to like a Jamico and I'd type in that part number and it'd bring up the specs on the 7-segment. The common, the problem is the common is usually toward the center. So right about in here, I don't remember what pin it is, but one of these would be the common on both sides. So if you got a meter, you could probably figure out which one it is. You could probably figure out if it's common cathode or common anode. But they usually run 2 common, so that way I can bring my voltage source on this side, or I can bring it on that side without swapping it over. So basically, I guess you could take your meter and just start measuring where you measure 0 between the 2, and that would give you the common. And then if your meter checks an LED, then you can find it that way, if you don't have a partner. So 7-segment displays. These big old jumbotrons, or these big old displays, they basically have a black background, of a black background, and they'll come in and they'll put 3 LEDs together, usually in a triangle. They'll put a red. I don't know if it's at the top or not. And then they'll put green. And then they'll put a blue. Oops, messed up my thing. Messed up. Green. So this is probably, have you ever got close to one of these things? You can actually start seeing the dot on the big old thing. So that's all it is, and then they can use these. So these are our super prime colors, red, green, and blue, and then black. And we can turn these things on in different variations, and we can get just about any color that we want. I hope I can find my magnifying glass.